Hi. Last lecture we have discussed about exclusive OR gate, special function gates. We have discussed exclusive OR gate. You can see this part, right? Up to this we have discussed. Let us continue with the remaining part of the XOR gate and XNOR gate and all. Okay. See here first. Before going to the exclusive NOR gate, one more condition in the XOR gate. Let us see. One important condition, X XOR with Y XOR with XY, this is equal to X plus Y. What is the condition? X XOR with Y XOR with XY is equal to X plus Y. Let us prove this. You take this as A, this total as A, this as B. Then what is A XOR B? A bar B plus A B bar. Is it okay? A bar into B plus A into B bar. I am taking this as A, this as B. From this, what is X exclusive or Y whole bar? Okay. See here. X bar Y plus XY bar whole bar into XY plus X bar Y plus XY bar into what is XY whole bar? X bar plus Y bar. De Morgan's property. Now here you can write this, take complement by duality property, X plus Y bar into X bar plus Y. Okay. And take individual bars into XY plus, now X bar into X bar is X bar Y, X bar into X 0, next Y bar into Y 0, Y bar into Y bar is XY bar. Okay. Now this is XY. Here you have X bar. You tell me X bar into XY. What is this? Or you can see here it is X bar plus Y into X plus Y bar into XY. X bar Y plus XY bar. Now you see here. Multiply this. X into X bar cancels. XY into Y. XY. Okay. Or one second. Better to expand this first. X into X bar 0. X bar into Y bar plus X into Y plus Y into Y bar is 0. Okay. Now you can take XY plus XY. What is the answer? One second, please. Yeah. X bar into X cancels. Y into X is XY. Y bar into X bar is this one. Y bar into Y is cancels, right? Now X into X bar again 0. Lastly, what is the leftover? XY only. X bar Y plus XY bar. Can I take X common here or Y common? You can take Y common. X plus X bar X Y bar. What is X plus X bar? 1. Y plus X Y bar. So Y plus Y bar X, distributive property, it is Y plus X. So what is the answer? X plus Y. So here one important point we should remember is X XOR with Y XOR with XY is equal to X plus Y. Right. Copy it. Please copy up to this. Okay. After copying that, please copy this figure. It is given in GATE 2016. Right. Now see. Suppose I ask you to find this function f. Don't do like this. Say for example, if you do like this, normally what we do, AB, BC, AB into BC. Okay, AB XOR with BC. AB into BC what? Okay. Then what is this? AB whole bar into BC. Like that, if you do it, it requires more time. So instead of that, how to do it easily, I'll show you. Here, up to this, okay, no problem. Here, see, AB into BC, nothing but ABC. Because B into B is again B. So what is the output here? Function AB XOR with BC XOR with ABC. Don't expand this equation and try it. Here simply same formula, X XOR with Y XOR with X into Y. X into Y, what is the X into Y? AB into BC is nothing but ABC. Then what is the answer? X plus Y. Or B into A plus C. This is the answer. Is it clear? This is like X, Y, X, Y. Because AB into BC, B into B is nothing but again only one B. So you can understand AB plus AB XOR with BC XOR with ABC equal to AB plus BC because using that property. Copy it. Right. Now, similar to exclusive OR gate, let us discuss exclusive NOR gate. What is exclusive NOR gate? Suppose if I ask you what is exclusive NOR gate, what is the answer you say? What is the exclusive NOR gate meaning? You can say immediately what is the answer you say is XOR XNOR is complement of XOR. That is wrong. XOR XNOR are not complementary to each other. They are complementary whenever you have two inputs. Okay, but when you have three inputs, it is not correct. Or I will give you the reason and all, but simply it is true only when your number of inputs are even. So 2 input case, 4 input case, 6 input case, XOR and XNOR are complementary. But when it is odd number of inputs, 3 inputs or 5 inputs, XNOR and XOR both are same. I will give you the property. Earlier we discussed exclusive OR gate. In the exclusive OR gate, what is the condition I have given? Exclusive OR gate is output is 1 when you have input में odd number of ones. Here if I say odd number of ones, you are getting output में 1. So if you take if your expression is like this, if it is even number of ones, my output is 1. If I say, then you can say it is complementary to previous. But XNOR function is like this. Whenever your input contains, observe carefully, whenever your input contains even number of zeros, that is the number of zeros is even, then in the input, not odd number, not even number of ones, please understand, even number of zeros, previously odd number of ones for XOR. Here, if your input contains even number of zeros, output is 1. Write down that point. Exclusive NOR gate. Exclusive NOR gate. Whenever the input contains even number of, whenever the input contains even number of zeros, then the output is equal to even number of zeros, then the output is equal to 1. Output is equal to 1. Now whatever we analyzed for XOR gate, same all conditions let us analyze for XNOR also. A, B. See, this is the symbol for A XNOR B. 0, 0, 0, 1, 1, 0, 1, 1. What is the condition I told? Whenever your input contains even number of zeros. How many zeros are present? 2. 2 means even or odd? Even. Here how many zeros? Only 1 zero. Odd. Here only 1 zero. Odd. Here no zeros. Assume it as even. No zeros. You can take it as a even. Okay. So here this is called A exclusive NOR B. You can see in this case it is complement to XOR but need not be same for all cases. I will prove it later. The expression for this is A bar B bar plus AB. I'll explain how to get the expression also when we discuss about the SOP and POS conditions. Now this is your Y equal to A bar B bar plus AB. Now see, this is the symbol for exclusive NOR gate. A and B, A XNOR B. You can understand here, one important point is, in the 2 input case, whenever input contains both zeros, output is 1. When input contains both ones, output is 1. So here we can say, whenever my input is same, okay, for both the cases, then the output is 1. Or you can also call this logic as another name, coincidence logic. Or another name is equivalence logic. Whenever both the inputs are same, output is equal to 1. What is this name? Coincidence logic or equivalence logic. These are the 2 names given for 2 input exclusive NOR gate. When both the inputs are same, then only my output is equal to 1. We call this as coincidence logic or equivalence logic. Right. Now see here. Already in the XOR case we have done few conditions. A XOR 0 like that. Yes or no? So same, let us do it for XNOR also. right? From the previous, we can easily say here also. So one of the input to the exclusive NOR gate is 0, how it will work? If one of the input is 0, other input 0, I am getting 1. Other input 1, I am getting 0. So you can say it is working like inverter. If one of the input is fixed to 1, other input and output both are same. So you can say it is working like a buffer or output same as A. A XNOR A. What is A XNOR A? A is 0, here also 0. 0 XNOR 0 or 1 XNOR 1. When both are same, what is the output? 1. When A XNOR A bar, when both are different, what is the output? 0. Here, A XNOR A XNOR A. So 3 you have. Now see here. A XNOR A. What is the answer? 1. 1 XNOR A. 1 XNOR A. What is the answer? A. Please understand. We have 3 A's. For 2 A's, you know the answer 1. 1 XNOR with A. So what is the answer? 1 XNOR with A. And if you can recollect, it is same as A XOR A XOR A for 3 input case. Last class we have discussed. So you can understand here clearly XNOR and XOR both are same when your number of inputs is 3. When the number of inputs is 4, let me analyze. A XNOR A. What is the answer? 1. 1. Similarly, this is 1. What is 1 XNOR 1? 1 XNOR 1 is 1. But earlier it is equal to 0. So it is a complement of A XOR A XOR A. So here very important case. When n is equal to odd, XOR is the same as XNOR. N is equal to even, XOR and XNOR are complementary to each other. This is the conclusion we should have. Whenever your number of inputs is odd, XOR and XNOR, both the functions will give you same answer. You can check, take 3 input case and try XOR and XNOR with the logic equation. What is that odd number of ones and even number of zeros condition, and check it, you get both of them same truth table. But if it is even number, they are always complementary to each other. So these are the conditions we should remember. Copy it. Okay. Now see, No need to write the, just understand. So you can understand, if it is 3 input case, A XOR B XOR C and A XOR B XOR C both are same. Say if it is 4 input case, even A XOR B XOR C XOR D is a complement of A XOR B XOR C XOR D and vice versa. So that is the relation between XOR gate and XNOR gate. What is the relation? XOR and XNOR are same when you have odd number of inputs, and they are complementary when you have even number of inputs. Okay, right. Now let us see what is the original relation between XOR and XNOR other than this complement condition. Okay, before going to that, let us have one example question. It is also a previous gate question only. Here, one important point we should note is A XOR B whole bar is nothing but A XOR B. For 2 input gate, we know that. It is equal to A bar XOR with B, which is equal to A XOR with B bar. Okay, you can understand here, I will prove this condition. For example, what is A bar XOR with B? First, you know what is A XOR B? A XOR B is nothing but A bar B plus AB bar. If you take A place mein A bar, take A bar here. Replace A with A bar. Then A bar whole bar is A bar, A bar, which is nothing but A XOR with B. Similarly, what is A XOR B bar? That is, firstly, you know A XOR B is A bar B plus AB bar. Replace B with B bar. Then what is the answer? A bar B bar plus AB, which is A XOR with B. Right. So you can understand now, it is clear A XOR B whole bar is A XOR B, which is A bar XOR with B, which is equal to A XOR B bar. With the help of figure, we can show like this. A XOR B whole bar is your A XOR. Now it is equal to A bar XOR with B this is equal to A XOR with B bar. Okay. This symbol, same symbol is given and they ask what is the function XOR or XNOR like this. Same question is given in Computer Science GATE 2013 paper. Okay. So these are alternate symbols for your exclusive NOR gate. Then you may have the doubt, sir, what happens if both the inputs A and B are complemented? Okay, you can check it. Take the function, take both A and B with complements, you can understand. Okay. So copy this. You can reverse this condition also. That is, here if it is XNOR here, then the functions will become XORs. Okay, what is the meaning? You can understand. If you have A bar XOR with B whole bar, which is equal to A XOR B also. Like that also we can say. It is not required, but we can find further also. Okay, this is one way to represent your exclusive NOR gate. Right. Now, after this, let us see how to implement your exclusive OR gate and exclusive NOR gate using your NAND gates and NOR gates. In the previous discussion, we have seen how NAND and NOR gates act as universal gates. how they have acted as a universal gate by using, you can say, we have implemented AND gate, OR gate and inverter also. But now let us see the same NAND gates and NOR gates. Using that, let us implement your XOR gate and XNOR gate. Let us see. You can make a note, write down. Implement XOR and XNOR gates. Implement XOR and XNOR gates using minimum number of 2 input NAND gates, using minimum number of 2 input NAND gates and NOR gates. 2 input NAND gates and NOR gates. So what is XOR gate? A bar B plus AB bar, right? We know that. Now let us use this function. Let us implement this function using NAND gates and NOR gates. Let us see. I am adding, for our convenience, A into A bar, B into B bar. What is A into A bar? 0. B into B bar? 0. Now see here. In the middle two and first and last, we can take B common. A bar plus B bar. In these two, we can take A common. B bar plus A bar. Then B into A bar plus B bar is AB whole bar. A into B bar plus A bar is BA bar. Okay. Now, otherwise, one second. You can take here A plus B common into A bar plus B bar. Same coefficients are same. So this is one way to represent your XOR gate. Another way is, now A plus B into A bar plus B bar. Suppose you want to make it using NOR gates, this is sufficient. But suppose I want to make it using NAND, for example. I should see only dots. I should not see plus. Let us see how to eliminate these dots. Take double bar, which cancels. Okay. Now De Morgan's X into Y whole bar is X bar plus Y bar whole bar. Now one second. Now, firstly, for easy understanding, A bar plus B bar can be written as AB whole bar. So I rewrite the equation as AB bar into A plus B double bar. Now, what is this function? Take this double bar as it is. AB bar into A plus AB bar into B. Okay. Now De Morgan's property, X plus Y whole bar, AB bar into A whole bar into AB bar into B whole bar by De Morgan's. Now I am seeing only dots here, no pluses here, only dots are seen here, yes or no? Now see here, how many gates are required? Okay. First I am making using NAND gate, then I will show you NOR also. What is this? AB bar into A into B whole bar. Okay, into A whole bar. So A into AB bar whole bar. Here this is B into AB bar whole bar. You can understand, because AB bar is common in both. No need to take two gates. Same expression we can use. Now this into this whole bar. which is nothing but A XOR B according to that expression. So how many gates are required for me? Minimum 4 NAND gates are required. Let us do that with the NOR gates. Using NOR gates. That expression, plus expression is there now. What is that expression? A plus B into A bar plus B bar whole bar whole bar. Now let us apply this De Morgan's law, x into y whole bar. What is the answer? A plus B whole bar plus A bar plus B bar whole bar. So now you can see here, if you take A and B, OR operation, inverter, I'll get A plus B whole bar. How to get A bar? Take A, inverter using NOR gate only. How to get B bar? Take B, inverter using NOR gate only. Add these two. Then A bar plus B bar whole bar. Now this plus this whole bar. Which is A XOR with B. Okay, here how many gates? 1, 2, 3, 4, 5. Okay. Now one important condition we need to discuss. What is the relation between XOR and XNOR? See here. What is A XNOR B? AB plus A bar B bar, this part already I have given. Can you tell me what is the dual of this function? It is A plus B into A bar plus B bar. Now you observe, is it same as this function or not? A plus B into A bar plus B bar. What is the value? What is the meaning of that? Which is nothing but A XOR B. So you can understand the original relation between XOR and XNOR is, what is the relation between XOR and XNOR? They are dual to each other. XOR and XNOR are dual to each other. That is the main important point. Okay. So first please understand, first copy this analysis up to this. After that please copy this duality condition. Okay. Then I'll give one point. First only copy this part up to this. Then copy this lastly. Copy it. Now see here. I'll ask you one question. First, suppose we have a function. In that function, if OR gate is replaced with AND gate. If we have one function, all OR gates are replaced with AND gates and all AND gates are replaced with OR gates. Then what is the function? The function will be replaced with its dual. So using that, see here. In this figure, if I replace all NAND gates with NOR gates, then what happens? This function will become its dual. Yes or no? If you replace all NAND gates here with a NOR gate, then this function will be replaced with its dual. That is, the dual of this function is nothing but exclusive NOR gate. Similarly, in this function, if I replace every NOR gate with a NAND gate, then what happens? This XOR will become XNOR. Please write this important point. Write down, since XOR and XNOR gates, since XOR and XNOR are dual to each other, since XOR and XNOR are dual to each other, if NAND replaced with NOR, if NAND, don't write replaced, write down, if NAND exchanged with NOR, then XOR will be replaced with XNOR. XOR will be replaced with XNOR in the above figures. Because in the above figures, that's sufficient. In the above figure, right? See here. Now you can understand. Please listen here. Say I am using NAND gate. Okay. Just now we have discussed what is XOR gate. This figure you should remember, we use it later also. A and B. This one is A XOR B. Now, using NOR. What I am saying is, if you take this same figure, but every NAND gate replaced with NOR gate. Same figure only. Here, there A XOR B. So here it will be A XOR B. Because NAND replaced with NOR, the function will be replaced with its dual. So here, this is exclusive NOR gate. Already we have done XOR gate using NOR gate, but here I will go by another way. That gate requires 5 only. Here, this is XNOR. Na? This is your XNOR. One second. If you give A and B, here what is the answer? Just now we discussed A XNOR B. Just take one inverter here. It will become A XOR B. Here also 5 gates, previous also 5 gates. So it is also useful. Now, in this figure, please understand, in this figure, replace every NOR gate with NAND gate. Same figure or not? In this figure, Every NOR gate I replace with NAND gate. Then here what is this gate? XOR. Then here it will become dual XOR. So these are the final conclusions of XOR gate and XNOR gate using NAND gates and NOR gates. Here how many are there? 1, 2, 3, 4. Here 5. Here 5 and here 4. If you remember the first figure, that is sufficient. You can make all other figures by using duality property. Now, so let us take inverter, AND gate, OR gate, XOR, XNOR. How many number of NAND gates required to make this? NOR gate requires XOR gate, okay, all to make all these gates. Already we have discussed in the previous lecture. Minimum NANDs required to make NOT gate 1, AND gate 2, OR gate 3, XOR. How many NAND gates are required to make XOR? To make XOR, I need minimum 4. To make XNOR, I need minimum 5. You can remember very easily. To make a NOT 1, AND 2, OR 3, XOR 4, XNOR 5. Here, because of duality property, it will be like this. This is also you can remember easily. Here one NOR gates 1 here, 3 here, 2 here, 5 here, 4 here. You can check in your notes this part already we have discussed. This we have discussed just now. So this table is important, especially XOR, XNOR, minimum number of NAND and NOR. They have asked so many times in all previous competitive exams. So very important. Copy it. Okay, right. That is about your exclusive OR gate, exclusive NOR gate. It will finish your complete logic gates. Okay, in the next lecture, we'll be seeing what are the different, let us see some problems based on this previous NAND gate, NOR gate implementations, and we'll see some alternate logic symbols, two-level logic, whatever the remaining part of this logic gates part, we'll see in the next lecture. Okay, thank you.